Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So welcome. This is the very first of our little tutorial sessions. Obviously, I hope you know where you're at. We're going to talk about cloud computing today, which is a really kind of a new area for Microsoft and quite a big investment for us as well. And I hope that it's something that benefits not just the business partners that Microsoft has, but it's also a good play for science as well. My name's Jared Jackson. Christoph is right here. We're going to be talking about how cloud computing frameworks can benefit research. We're both from Microsoft Research. Until about 2 weeks ago, we were both from the external research team as well. I moved just a couple weeks ago to a group called the Extreme Computing Group, where I'm going to be working on cloud a lot more as a dedicated thing. This is basically the outline of what we're going to do. We're going to start, I think, real quickly just to introduce some basic concepts around clouds and data centers. Because it's the data center really that is the kind of the hub, the reason why this all economically makes sense, why it's probably a good model to use. We'll only do that for about 10 or 15 minutes, at which time I'm going to turn the time over to Christoph, who's going to talk about Dryad and Dryad LINQ, and he'll explain what those things are if they're not familiar to you. And then I will, we'll probably do a little break after that second part too there. We have 2.5 hours here today. So we'll take maybe a 10-minute break, and then we'll jump into Windows Azure. I'll do the presentation at that point, and we'll go into the platform, how we can use it, and then we'll have some examples of it. And we've actually got some friendly folks from Newcastle University who will give us a little demonstration of a project they've been doing in the cloud with Azure and some other technologies as well. I actually have what I hope is a fun little exercise for us all to do during that Azure part too. All right, so what is the cloud? The cloud is kind of, it's a new concept in terms of us calling it the cloud, but it's actually, you know, anybody who's worked on large-scale data centers before or cluster-type computing understands that there's just some problems that have to be done. They can't be done by a single processor. They can't be done just by running something overnight. They require a framework for working across distributed data and being able to tackle problems that we need the solution to much sooner than a single computer could work with. The interesting thing about the cloud itself is that it's more of a platform as opposed to an infrastructure that you would have to manage on your own. So the idea now is that economically and also in terms of the amount of work you want to do, it might be a lot easier for you not to have to be the expert both in maintaining a data center, a cluster, and all the infrastructure that goes along with that. Instead, you can have a company managing that, a company or a nonprofit organization or anybody managing that system for you, and you just be able to make use of those resources when you need them. So the buzzwords you kind of see are IaaS and PaaS and SaaS. That's our as a service things. The infrastructure becomes a service. The platform, the software that makes that infrastructure work, and the software that then gets distributed across it is also a service. All those things are just either made available as a service for free to an academic through a grant of some sort, or maybe in some sort of model where you have to pay for the computing. There are actually quite a few areas. Oh yeah, thanks. There are quite a few areas where the science can use this, and it's not just physical sciences. We're finding that sensor networks that are out there that are actually creating data, maybe oceanographic data that gets pulled in, or astronomical data, telescopes, the LSST is taking pictures of the night sky. those aren't the only things that benefit from cloud. You can actually have the humanities as well when you're doing natural language processing or trying to make archives of historic literature. All of these things benefit not just from the computational power that the cloud offers you, but the software storage as well. And you can not only archive that stuff out there, but create nice searching tools so that you can get at the information when you need it and not necessarily have to have that on site. Obviously, the driving reason why companies like Google, like Microsoft, like Amazon are putting these together is that there is an economic model here that makes sense for those companies to host these services and then charge for them, but also for the people using them. Businesses, may have, say if you're a web retailer, a lot of your traffic comes in December or November when the holiday season is around. Well, maybe you need 500 servers working at that time, but through the rest of the year you only need 50. Well, a data center scales up easily for that. Similarly, for scientific applications, if you consider you're working on some interesting algorithm to analyze, an AUV track, a robot that's running through the ocean, and it's picking up the salinity levels of that ocean, and you want to do a modeling algorithm across that. Well, it may take you a couple of months to get that algorithm in place, and then you want to run that algorithm. The couple of months while you're developing and testing the algorithm, you might not need that many servers, but when you actually need to get your result across, you might need something that the data center would give you, 500 nodes or something like that. But rather than having to host that inside of your building and have the, pay for the maintenance of it and everything during that time when you're not making any use of it, you have it this kind of economical way of instead just using it when you need it. So while the examples here tend to be a little bit more on the business side, and that's the justification for the companies, so there's also quite a good use on the research side as well. There's obviously you can use the cloud for storage, and the other nice thing about the distributed model of it is you can take existing applications, things like MATLAB, and deploy them on the cloud as well. The next nice thing about the cloud is that it provides kind of a server architecture so that all the computation being done up there means that you can disassociate yourself from your own laptop, and if you're doing field work or you're just anywhere where you don't necessarily have the computational power you would normally need to do your work, we now have cell phones with enough computation power and access to the internet to be able to get the data and at least launch off whatever process you need to on the data which you've collected, and then be able to view the results of that. So by having that kind of software deployed up in the cloud, having all your analysis happen up there, and having it be a little more flexible on how you can see the results, by having the cloud, you kind of make it so you don't even necessarily need to be tethered to a laptop when you're going out and doing your work. You can have, a TV, if you happen to have that and it has a connection, your cell phone, your whatever future devices that happen to be coming, including things like, if there's mobile health sensor devices and you've connected to a database that's keeping track of your health records. It's actually, the future applications of this are quite interesting, because if we do something where, like the government is now looking at, we're keeping our health records up on the cloud, and you maybe even just have a bracelet with a chip inside of it, a hospital can get to your records. It doesn't have to necessarily even be your computation device, as long as you've got the access with you somehow. All right, so this is, I think, basic for everybody. We've described why we need why this is becoming an interesting topic of conversation. The cloud, obviously, we can't hit the scale that we need without it, and so the solution is to build these data centers. This is a picture of one of the data centers which we have built. Just to give you a sense of the scale on that, this little section right up here That's about the size of a football field. You see where they're coming in just in that little corner right there? So this data center is really quite massive. It's, you're looking at maybe, 15 football fields worth of size there. And so because of the data, the power consumption and the data input and output is so huge to come into these, the pipes that you need to go into these, that they pick locations that are both located near large power sources, maybe by hydroelectrical plants, things like that, have access that is a lot easier. They also pick it for tax reasons. They try and find areas that are beneficial that way. And all of that is to make it so that the economies of scale work out right. And then what you see here on this chart over here is a kind of a savings amount that you get by moving your networks into data centers like this, on the order of 5 to 10 factor in terms of cost that you can save. But at the same time, you need to have a problem that scales up this large, so you wouldn't start something like this for your particular lab. And we have several of these in the process. Oh, there you go. This is kind of interesting. Microsoft's actually been fairly open about the way it's putting its data centers together. It used to be that you would build these large buildings, and somebody just put racks and racks after computer, and those little pizza box-like computers would just fill all those racks up. Well, Microsoft's come up with a little bit of a more modular way of putting its together. They actually put all of the computers inside of a trailer, which they stick on top of a semi-truck, and they literally just back that truck into these hubs and plug the back of the kind of all these connections coming out the back here into a sitting hub that's already up there. Yeah, so this is the data center in Chicago. Basically, before it was hooked up, this is what you saw, is there's just kind of these little boxes here, and it looks like almost like a parking lot, where there's little yellow lines saying where the trucks need to back into. And all they would basically do is, you can see, they come in through the door, and this is how they're supposed to back the trailer right in there, and they actually stack them too deep, and then they just plug them in right there. And so there's no extra configuration. It's kind of just take it from the factory like a manufactured home almost, back it in and plug it in, and it's ready to run. Now you can get in there and access those. That's what comes in here. So if you need to do maintenance and pull things in and out, you can do that. But it's a lot more like you would build a manufactured home now than a custom one. And this Chicago data center actually just went online, I think within 3 weeks now, and they just did a tour, and that's where I got this picture from. All right, so this gives you a sense of the scale. There's the way the network is set up. There's about 800 nodes per cluster. So as they back one of those trucks in, there's about 800 computers sitting inside one of those things. Each one of those then has to talk to the other clusters around it in case you need to scale up or down. And in order to just kind of quickly go through these, we'll have these slides available, and you can go through the way that we actually set up the layers of communication. Obviously, that there is an impact on the environment. This much compute power, it's densely compacted, but it does take up quite a bit of power. The estimate in 2006 was that we were, just in terms, not just ours, but in all the data compute centers, we're taking between 1.5% to 3% of all the electricity used in the United States. So really there's an incentive, not just from a cost point of view, but from an environmental cost point of view, for us to figure out ways in order to make sure that when we scale up and down, that we're making sure we scale up the power use as well. Okay, so that was kind of just a basic introduction to the infrastructure behind clouds, why we're putting them together. What we're going to do now is talk a little bit more about the software, how you can make use of that. And Christoph's going to start with Dryad.
Mm-hmm. Thank you. I'm going to move that a little bit out of the way. So thank you, Jared, for setting the scene, and welcome to all of you. As Jared mentioned, when we look at today's data centers, there's basically a awesome amount of computing power in there. And if you're like me, I'm really thinking about, how can I take advantage of all that power to put it to good use. And so in the next two sections, we're going to take the point of view of the programmer and try to talk about what it means to compute by using those systems. In the latter part, we look at the Windows Azure APIs and platform. And in this part, I'm going to talk about systems that you may or may not have heard about, which is called Dryad and Dryad LINQ. So I'm curious to know a little bit about you, and I'm wondering how many of you have actually written parallel programs that use, say, 100 compute nodes or more. This could be MPI programs or MapReduce type program. Okay, so that's a good number. That's still okay, yes. And how many of you who have not had the opportunity are thinking of maybe going that way because you have a problem that you want to scale up and you would like to have the ability to do that? So that's a few more, so that's good. That's interesting. So today I'm going to tell you about Dryad and Dryad LINQ, which are two systems which come out of a research lab in the Silicon Valley office. And the combined goal of Dryad and Dryad LINQ is really to make distributed computing accessible to most programmers. So it's one thing to have one very talented expert being able to program such system, but really if we want to take advantage of that at massive scale, we really have to enable the everyday developer to take advantage of that. So what I'd like to do today is introduce Dryad and Dryad LINQ and first of all set the stage of where the problem comes from and looking at data-intensive problems. Then as we end the session, what I hope you will get out of it is an understanding of what those two systems are and how they leverage the .NET framework to really make writing a distributed program feel like writing a sequential program. And also, I will give you some examples of applying those frameworks to solve problems in the space of science. And so hopefully you will see that those systems have a potential to be applied in the scientific domain. And maybe you'll be curious enough that you'll want to actually download the software and try it for yourself. And if you do that and you can give us feedback, then we can have a good dialogue to move forward. So let's start with the motivation. And as Jared already mentioned, and I'm sure many of you are facing that or are familiar with that at least, is that data-intensive computing nowadays is very prevalent. In many domains, acquiring data using experimental apparatus or sensors is very easy. Storing that data is very easy. We also have simulation capabilities which can generate huge amount of data. And the problem then becomes, how do I analyze the result of my simulation? And then there are other sources. There's literature, there's the web, vast amount of data that people want the ability to process. But what's interesting to note is that even though the computing power has increased, there has been some disparity in how that evolution has happened. So for example, if we look at storage, it's very cheap to store a lot of data. But reading and writing to disk is actually very slow. The rate of I/O has not increased as fast. Similarly, if we look at what we could call commodity hardware or your typical workstation, the RAM that you can have on a typical workstation will typically be between 8 and 30 gigabytes, which is a lot compared to what we used to have, but it's still a stringent limitation on how much data you can process in memory at the same time. And we talked about the I/O. So the net conclusion there is that even though the computing power has increased dramatically, there are some challenges when you have a lot of data in order to process that data. Fortunately, there's a solution that has appeared, and you've probably heard about MapReduce, which has been made popular again by Google in particular. The idea there is that if you have a massive data set, instead of trying to funnel all that data into one machine, which becomes a bottleneck, can you actually take that data set, break it into pieces, and have those pieces being processed independently by a single program? So it's something that people refer often as multiple data, one single program. So not all problems will fit into that category, but there's actually a large class of problems that can fit in that category. And the net there is that if you have a large amount of data, if you only have one hard drive and you need to read all that data, it's going to take a long time. If suddenly you have 1,000 machines and 1,000 hard drives or even more hard drives, then you can reach a throughput which is quite dramatically higher. But there's one catch. Even though programming at scale seems like it's feasible, it's actually very difficult to do. Because as you increase the number of machines that you have in your system, there are some challenges that come in. One of them is the more machines you have, the more disks you have, the more failure you are going to encounter. So therefore, you need to be able to deal with failure and have a program that can be robust in spite of the network going down or a hard disk not being able to function. In addition, there's the challenge of deploying the application, but the greater challenge too is writing the application, having a framework that allows you to do that seamlessly. So fortunately, as I mentioned, there are ways out of that. Maybe some of you have been part of the CLUE program, which IBM, Google, and NSF have carried out to give clusters and then using the MapReduce framework from Hadoop. What I'd like to talk today about is a different approach that we've taken at Microsoft, which really leverages the Microsoft.NET framework to try to make the programming a lot easier in our mind. So that is the goal of the Dryad LINQ project. And the real goal there is to say, can we find an environment that people are familiar with and in which they can write a program which looks completely like a sequential program, that you can debug to some extent like a sequential program, but when it comes to its execution, it's actually running on a cluster which could be small or very large. So what the Dryad LINQ program is trying to do is leverage the .NET framework and all its ecosystem, for example, Visual Studio, although it's not a requirement, let you work in that environment where you write your program, and then in the backend, seamlessly, some things happen such that parts of the program that can be distributed, are sent to a cluster where the computation happens much faster, and then when that is done, the result comes back to your program, to your workstation. So one key way in which Dryad LINQ attempts to achieve that goal of giving the appearance of a sequential program is by leveraging the .NET framework, and in particular a technology called LINQ, Language Integrated Query. What LINQ is trying to do is really make writing queries, so manipulating data, a first-class citizen in the programming environment. LINQ was introduced in the .NET Framework 3.5, and it benefits from Visual Studio and the environment that Visual Studio provides, but it's definitely not a requirement. At its core, LINQ is an interface. It defines operators that you use to manipulate the data. And if you compare that to SQL, some aspect will feel familiar because you will find operators like the select, join, group by, even things like count and so forth. But one key difference is in the language. SQL, I think it's fair to say, is a fairly restricted language, or if you want to take full power of it, it becomes quite an intricate language that you have to master. Here, we have the ability to query data using a programming language, for example, C#, which a lot of programmers are already familiar with, and then they can leverage that knowledge, and just by learning a little bit more, they can write their queries. And also, they can take advantage of the environment that is provided by the .NET environment, meaning that instead of working with SQL data type, you're actually working with SQL objects. So you have a very strongly typed data model, and you have the ability to call functions which are within your program. So it's much more expressive and much more extensible. And LINQ also has a platform is designed to be extensible, and we'll come back to that in a few slides. So if you've never seen LINQ, this is what an example program would look like. And this is actually a C# program. How many of you are familiar with .NET languages, C# and so forth? So quite a few, so that's good. So I'm just going to walk you very quickly through that query so that you get a sense of what it is. So the first line over there, get log lines, basically is giving you a list of lines in a log file. And it's a collection of strings. The I enumerable represent a collection. So the first step of the query would be to go through those lines, so from line in logs, and then in that log, every line that starts with a hash is actually a comment, something that we don't care about. So we would just use the where operator to filter those lines out. And when I talk about working with strong typed objects, that's what we do next. So for the line we want to keep, we actually transform them into an object that we've created, a log entry. The log entry is just a little object which takes a line, splits it into parts because we know the structure of the line, and extracts out some fields out of them. For example, a username, a page, a web page which was accessed. The next step of the query then keeps going. Wrong way. Having that list of log entries, now we only want to keep the one which refer to accesses by a certain user. In that case, the username is hardwired. It's Ulfar. And so that gives us all the lines which are referring to accesses by that users. And then we keep going and we find the web pages which have been accessed by that users. And now we use a group operator to group all those pages together. And then finally, the last part of the query, the accesses, is just taking those groups and aggregating the result so that for that user, we know how many times he or she accesses that web page. And then we order them so that we get the result from highest access to lowest access. So hopefully that gives you a feel of what LINQ is. And when we talk about language integration, it's really all those keywords, the var, from, in, where, var, order, by, which could look like syntactic sugar, and they are to some extent, but really they're there to make writing the query a lot easier and to boost your productivity. From an architecture point of view, this is what LINQ looks like again. So on the left side, you have your .NET environment where you write your program. And then that blue bar really represents the LINQ interface, the LINQ API that you program against. But as I mentioned, LINQ is really designed to be extensible so that you can plug in a lot of what they call provider, which really are execution engines that can take a query, go to a specific data store, do whatever operation is necessary to return the result of the query. And there's a lot of different providers that are actually providing. One of them is LINQ to Object, which allows you to work with objects in memory. LINQ to SQL, of course, to access SQL databases. And then we will revisit plink in a little later in the presentation. And of course, Dryad LINQ is the one that is of interest of us today. It's just a LINQ provider which can take a query expressed in C# and LINQ and can have it execute on a cluster. So in order for that to happen, there are a few things that Dryad LINQ adds to the programming model. And the main extension to the programming model is really that notion of a partition table. It's essentially a collection which is not restricted to one machine, but is distributed over many machines. So you can think of it as a partition table as a metadata that describe one collection, but that collection is made up of parts, and each part sits on a physical machine somewhere on the cluster. Outside of that, like I said, Dryad LINQ really is a faithful implementation of LINQ. So it implements the majority of the LINQ operators. And in addition, it adds a few operators which you would not find normally, which are mostly to deal with partitioning the data over a cluster. So that if you start with one monolithic file, for example, that you get from an application, and you want to break it into parts over the cluster, you can use a range partitioning or hash partitioning scheme. And then there are a few other operators like apply, fork, and materialize, which are for advanced uses, and we will not have time to get into those today. So if we revisit the log query programs that we just saw in LINQ, in C#, and you wanted it to be a Dryad LINQ program, this is what it would look like. And really, the core of the program here is the same. It's what we looked at earlier. It does not change. I've added on the side the two little helper classes that we defined, that define a typed object. Again, those do not change from a single machine implementation. The key is really how we get the lines that we're going to process. So at the beginning, you see that we have a partition table, which is a collection of strings, and we use the partition table get operator defined in the Dryad LINQ API to just instantiate that collection. And then at the end, we actually save the result, in this case, to file. Or if you know that you won't have a lot of results, you could do like a for each loop to iterate over them. It's worth pointing out that if you were to execute the program in the debugger and came to that point, nothing would happen. And it's because one feature of LINQ is that queries are deferred, meaning that execution doesn't happen until you ask for the results. So what happens when you run the program up to here, it's really the program is building a tree which represents the query, but it's not until we try to materialize the result that some execution will happen. So at this point, I wanted to switch into a demo. Unfortunately, I cannot connect to my corporate network today, so I'm going to have to revert to a backup plan. But what I wanted to show you is exactly that log query running so that you get a feel for it. Now, the Dryad LINQ and Dryad system can run on top of multiple type of clusters. And the one I wanted to show to you today is Dryad running on top of a Windows Server HPC server. Now, since I cannot show it to you, I have a little movie, however, that I can play, which hopefully will give you a similar feel. So this is showing what, and it's probably small for you in the back of the room. Right, but unfortunately I can't really make it any bigger than that. This file over there is basically a partition file. It's a metadata that describes a partition, and we just look at a part which was just a small piece of text. What we're running here is essentially the hello world of distributed computing. We have a set of text, and we want to find the words in that text and count how many times they occur and find the word that occurs the most often. So if I back up a little bit using the movie here. You see that over there I'm launching my program which has been compiled. That's running on my workstation. And then Dryad LINQ has taken my query and has printed a query plan. And then on this pane here, we're looking at the HPC job manager, which shows what's happening on the cluster. And you can see that some tasks are being queued in my job, and the first set finished, and then more tasks were queued, and then another one finished. And then eventually the job finishes. And if we look back at the program running on the workstation, then control will get back to that program, and we will print out the result of the evaluation. So really what we have here is two systems working together. A program which was written in a .NET language, which is a sequential-like program, and its execution ended up triggering events on the cluster where the actual core of the computation happened. So in the log query demo that I wanted to run, the point was to show how you can get a 10 gigabyte file, which if you were to just read it on this laptop here would take almost 5 minutes. But by being able to use 10 nodes in the cluster, we can actually do the entire log query in a matter of 20-25 seconds. Now, one question that comes often when we talk about Dryad LINQ is the fact that we have to partition the data so that we have that partition table. And one of the questions that comes often is, how do I partition my data? One way that people do it quite often is actually use Dryad LINQ to achieve that purpose. So in the example of the log query, what I did is I started with a file which was 10 gigabytes. It was a monolithic file. And then I wrote this Dryad LINQ program to basically invoke a function which reads the monolithic file and then uses a hash code, in this case the hash code for each line, to create beans of lines. And then I decided that I wanted to have 10 such beans because I have 10 nodes in my cluster. And so by just running that Dryad LINQ program and materializing the final partition table, I'm able to do that distribution of data. And it's a common case that people will do that. They start with some data, they run a Dryad LINQ program to partition the data, and then they write many more Dryad LINQ programs which are their analysis of the data. So you have a first data set which has been partitioned that does not change, and you analyze it many times. So let's, now that we've seen it in action, let's try to sort of deconstruct the system a little bit and see how it works. And it's useful to start with the stack of applications that we actually have. At the very top, you have what the developer is writing in the application space. And at the bottom here, we have the cluster services. As I mentioned, for Dryad and Dryad LINQ, the cluster can be of different type. It could be the Windows HPC, which is a product by Microsoft. It could be Cosmos, which is a cluster implementation which is internal to Microsoft. And in the future, for you, it could be Azure. We already have a version working internally, but it's not public yet. On top of that cluster, we have Dryad, which is our execution engine. And Dryad, besides being able to rely on multiple cluster services, can rely on different storage services as well. Again, it could be SQL Server, it could be the file system, it could be the cloud. On top of that, there's a Dryad LINQ layer, which enables the communication between the application and the cluster services and Dryad. So let's focus first on Dryad. The way to think of Dryad is as a very general engine to run distributed computation, which are described by a graph, by a DAG. Dryad is not really new. It's been developed since 2006, and it's really been used. The incentive for developing Dryad was really the search business. So how do we serve search to our consumer, and how do we enable that? So it's been used by the search group. It's running on very large clusters, which can reach the 10,000 machines and processes large amounts of data every day in the petabytes. And as I mentioned, it's been developed by the Microsoft Research Office in the Silicon Valley. And there's an active group of users at Microsoft. Another way to think of Dryad is a generalization of the Unix pipes. So if you're familiar with a Unix pipe, you have maybe some input data that you want to process, and you're going to pipe it from one operator to another until you've achieved the transformation that you desire. But you can think of that as a one-dimensional process. It happens on one machine. Dryad sort of takes a two-dimensional approach of that. You still have input data, but instead of having one, you have multiple. And then you want to process that data by pushing it through operators. But again, that's where the two-dimension comes about, is that instead of having, for example, a single instance of the grep program running, I may have 1,000 instances running in parallel. And then that data will then get fed into a next step, which in that case is SED. And there I may have only 500 instances of that because there's been some amount of reduction or for some other reason. And then you go on and go on. So the net of that is that if you want to execute a job with Dryad, you need to describe your job as a directed acyclic graph. And the terminology that Dryad uses is as follows. Of course, you have your input file at one end and the output files at the other end. And in the middle, the nodes of the graph are called vertices. Essentially, they're processes. And those processes are connected by what they call channel. Channel really represents a flow of information. And channels can take different types. They can be implementing using the file system, so where you write to a file, read to a file. They can be in-memory queues or TCP pipes, sorry. Now, once you've described that job as a graph, you hand it out to the Dryad execution engine. And very rapidly, this is what the architecture of it looks like. The key part here are the job manager on this hand, which is one process which really takes out the definition of the graph and then manages its execution. In order to do that, the job manager needs to know what resources are available in the cluster, and that's why there is a name server that hands out that information about the cluster. And then finally, on every compute node in the cluster, you have processes which can instantiate those vertices when the job manager requests it. And then they can report back to the job manager about their status. So that's the execution layer, the daemon launching the vertices. And then at the top, there's really that data plane where data is transferred and the channel linking the vertices. Now, in this case, we see the job manager running on what looks like a workstation. And depending on what cluster services, that can be the case. In the case of the HPC implementation that we just showed running, the job manager always runs on the cluster. And it's actually, in an HPC job, is made of tasks. So for Dryad, the first task is always the job manager. And then the subsequent tasks represent vertices. Now, you may say, is that all that Dryad is about? Yes and no. In fact, Dryad adds some properties which are very beneficial when you deal with very large systems. One of them is fault tolerance. So as we mentioned, the more nodes you have in a system, the more likelihood that a failure will occur, whether it's a machine or a network. And so Dryad can effectively deal with that. For example, in this example, we have a little animation that shows a machine going down, so the process dies. So if you don't have an engine like Dryad, then your program will fail. And you can see how writing robust program would be difficult. With Dryad, the fact that we have a DAG representing the job means that if a failure occurs, the job manager can be made aware of that, and then it can back out and reschedule the process on a different machine. And so there you have two outcomes. Maybe it will fail again, and then Dryad has policies to decide how many times it should retry, or it will succeed, and then the job can go on. A different kind of failure is when a channel fails. So in this case, the data did not make it to the next vertex. So what we need to do then is back out one vertex and then reschedule it so that we can regenerate the data. And that's where you can see that having a job described as a directed acyclic graph is very helpful because it implies an ordering on the operation, and you can always, when you have a failure, back out and restart. Another property of Dryad is one of data locality. If you deal with problems that have to read a lot of data, it's very important to try to put the process that will read a piece of data on the same machine where that data is located, because that's where you will get the best performance. So again, Dryad knows where the data is located, what process needs to read that data, and if it has information in addition about the cluster, the topology of the cluster, knowing how the nodes are grouped into one pod and how the pods are related together to form an entire cluster, it can optimize to make sure that, to the extent possible, processes are co-located with the data. Now, there are other properties to Dryad, and in fact, it's still a very active research project. Like this week, they're presenting their work on scheduling, a scheduler called Quincy, which is quite advanced. And we don't have time to go into all those properties. But one key feature of Dryad is that even though it's a powerful engine, its programming API is fairly low level. And the researcher put out a C++ API, and they thought that if the API is there, people will come and program to it. But what they realized is that it didn't quite happen that way. It was really difficult to have to describe the entire job as a graph. And so that's where Dryad LINQ came about. The realization that Dryad is powerful, but is not easy to program. Can we leverage .NET and LINQ to make that easier? So what Dryad LINQ does then behind the scene is quite a bit for you in order to give you the illusion of the sequential programming model. First of all, it has to look at your program, define what the data is. So we've talked about the partition data. Then it has to be able to interpret your query. So the code that you've written in C#, F# or VB using LINQ has to be translated into a Dryad job. And so that's the job of the Dryad LINQ provider, is take the code that represents your query and build out of that a Dryad job, which then gets shipped to the Dryad execution engine. Now, it doesn't actually end there, because your code may rely on some functions which are part of the Dryad LINQ and Dryad stack, but most likely you have custom code that you've written that also needs to be shipped to the Dryad engine so that it can be executed there. So there's quite a bit of logic in Dryad LINQ to analyze your program and extract the information that needs to be extracted. So all of that gets shipped to the clusters, and Dryad LINQ invokes Dryad, the execution runs, and if it succeeds, you get the output being generated, and that can feed back to your Dryad LINQ program. So let's dig a little bit deeper into the query plan. And let's use again that word count example, the one we actually saw running today, which is a classic problem where we have a lot of documents. Out of those documents, we want to extract words, and then we want to find the words which occur the most often. So the way to represent that program in LINQ, and here this is using the function notation. It's not using the additional syntax that LINQ provide. You see that what we need to do is we need to go from document to words, and then use the select menu to get a collection of words. Then we use the group by operator to group the words which are similar in collections. And then we aggregate those collections by just keeping a pair where the key is a word and the value is the number of instances for that word. And then we, in this case, just output the result. So when Dryad LINQ interprets that, it actually creates first a simple plan which has your input data, a select menu operator, a group by operator, a select operator, and then the output is generated. From that plan, it's able to generate the Dryad job. And we show here the actual job that happens. Now, if you pay attention, you may notice that there's a bit of a disparity here, because even though we have 5 nodes in that linear chain, when we get to do the execution on the cluster, we actually have only 4 stages. So why is that? It's actually because Dryad LINQ has done further optimization before sending the plan to the cluster. So to give you a feel again of what that is, this is what's actually happened. For the select menu, there's not much we can do. We have to read the data and just get it out. But when it comes to the group by, there's actually optimization that Dryad LINQ can do in the same way that databases are full of tricks and optimization. So one key aspect here is that Dryad LINQ realizes that at the end of it, since we want to get the count, the number of words, we have to do a sum. A sum, it turns out, is associative and commutative. So instead of just delaying the sum till the end, which means that we would have to carry all the data before we can count it, what Dryad LINQ will do is actually do a count early on, so that we can locally do a partial sum and then really reduce the amount of data that we have to carry to the next stage of the job. So there's really a lot of aggregation and a lot of optimization that happen. In addition, the other optimization that we see is that Dryad LINQ takes into account pipelining. So even though we have about 8 different individual processes, what we could think of as individual processes, if each of them was an individual process and we had to carry data from one process to another and start a process each time, it would be much more less efficient than what we're going to do now, which means to say that to the extent possible, we are going to take those operations and group them into what we call a stage, so that we actually only have one process running those different steps. So in the end, we end up with 2 different vertices, 2 different processes. Within each one, we can do a lot of operation in memory, and we only have to pass data from one machine to another in one instance instead of many. So that's why in the end we end up with that plan. So if you were to look at the Dryad LINQ files that get shipped from the workstation to the cluster, you would find that there's some XML files. This is an example of it, which actually describes the query plan, describing what a vertex should do. You can see there are some DLLs which are being shipped. It's really all the dependencies that needs to go from the workstation to the cluster. As a user, you don't have to think about it, so it's nice to know that all of that happens automatically. And then if you were to dig deeper, you would see that in the case of this program, Dryad LINQ also generated some code on the fly, which is the code for the vertices. So this is for one of them, and you'll find that you have the sort ordered group by, so you can actually sort of match that to your query. But sometimes your query and what you see here, there's quite a bit of discrepancies, and it takes some thinking to really match the two. Now, a few more words about Dryad LINQ. I'm sure a lot of you have heard about MapReduce, and this is what MapReduce looks like in Dryad LINQ. It's really three lines of code. So, which means that just like in Hadoop, if you want to do MapReduce, you just install the framework, and all you have to worry about is writing a mapper and a reducer. In Dryad LINQ, you can use that helper function, and then to do your MapReduce operation, what you need to do is provide 4 things. Of course, the source, which is the input data, a sequence of objects. Then you need to provide a function, which is your mapper, to transform your objects into another type of objects. A key selector to say how you want to hash your objects. And then a reducer to do the reduction. And if we had more time, we could go into the detailed plan that gets generated out of that. And again, there are other optimizations that Dryad LINQ does to make the execution more efficient. So let's come back to conclude to the Dryad LINQ architecture. One benefit of Dryad LINQ being part of that family of LINQ provider is that it can take advantage of other features that are integrated into LINQ. So for example, PLINQ stands for Parallel LINQ, is a library which allows you to take a LINQ query and really parallelize it seamlessly so that you can take advantage of the many cores on one machine. Well, in Dryad LINQ, you can also take advantage of PLINQ. There's a flag that you can enable in the Dryad LINQ configuration. If you set it to true, then Dryad LINQ will not only distribute the computation on the cluster, but on every machine, it will invoke PLINQ to take advantage of the many cores available on that machine. Similarly, we've seen an example that works with file, but the data can reside in different storage. So for example, LINQ to SQL is something that has been explored. And finally, there's LINQ to object. LINQ to object allows you to work in memory, and you may want to think, why is that applicable when we talk about distributed computation? Well, it's actually very useful when you are debugging your problem, because you can just set a flag in Dryad LINQ to say local debug is true, and then the Dryad LINQ provider then switches to, instead of going to a distributed system, to everything being linked to object enabled, so that you can actually do your debugging, see where your problems are, and then turn the flag back to no local debug. So this concludes the overview, and I now want to give you a few examples of how Dryad LINQ has been applied to science problems. But before I do that, I'd like to put Dryad and Dryad LINQ in context. There's quite a wide ecosystem out there, and a lot sometimes of controversy about what system people should use for certain problems. So we should really acknowledge that and say that there are multiple solutions out there. On one end, we have the databases where they provide everything, the storage, the execution, and the language. Examples of that are Postgres, Oracle, DB2, Teradata, and some more. Databases are really very powerful execution engine, but when they tend to fail, I guess, is in the language that they provide, which can be powerful, but it requires a deep knowledge of the language, and SQL is often acknowledged as not being the best language of all. Another issue sometimes with databases is that they really do require some tuning and optimization and expert to do that. So there's quite a bit of time that you need to put up front in order to get the good results. At the other end of the spectrum, there's MapReduce, which has been again popularized by Google, and then there's the Hadoop version, which is open sourced, which came from Yahoo. And it's kind of the opposite of the parallel databases, where they go for extreme simplicity. So you can get a system running and solve a problem very quickly. But because of the simplicity, you have to deal with a very low-level language, and that is somewhat of a problem. And also, it's not only the language, it's the fact that you can only do map-reduce, so everything has to be a map-reduce problem. Of course, to address that problem, there are some languages which have been developed, Sozol, Pig Latin, and also Hive, which is more like a SQL environment. And so we get better languages, which is good for the programmer, but the downside of that is that because still everything has to be a map-reduce problem, you get an execution which is not as efficient. And so at the end of the spectrum, even though there are a lot of similarity, we have the Dryad LINQ stack. And I also added Scope, which is, again, a language which is internal at Microsoft, but which is somewhat similar to Hive, which has a SQL-like language to interact with Dryad. So why would you choose Dryad LINQ? Well, I hope you've started to see that it's really the intuitive and ease of use and the ability to write a sequential program, or what looks like a sequential program, but it's actually a distributed program, and benefit from the ecosystem that the .NET platform and its tool provide. Furthermore, if you wanted to try it for yourself, well, you actually can. Since July, we have put out a free download on the Microsoft Research website where you can have Dryad and Dryad LINQ, and you can install it on Windows HPC clusters. This download comes with tutorials, programming guide, examples to get you started. And we also have a site on the Microsoft Connect where people are welcome to submit issues. There's an email address where people can ask questions, and we would welcome everybody's involvement. Now, the last thing you may want to know is, how has Dryad LINQ been applied, and does it actually work? So within Microsoft, in the past few years, there's been a lot of researchers using Dryad, and mostly through Dryad LINQ, and they've applied that to a lot of different areas that go from clustering, image processing, search. So essentially, a lot of the things that you do, which are sort of web-related, your PageRank algorithms and so forth, but also some machine learning and optimization. And recently, we've tried to work with people outside of Microsoft to see how can we apply Dryad LINQ and Dryad to scientific problems. So I'm going to give you a few examples of that. The first one I'm going to give you is actually an astronomy example, which we did internally, which is query 18 in the Sloan Digital Sky Survey database. It's one of the most time-consuming query to do with the database. And when we applied it using Dryad and Dryad LINQ, we observed that we could very quickly solve the problem in under 2 minutes with 40 nodes. And the scalability was really good. What's interesting here is to see that as you use Dryad LINQ, which is a red curve here, you get the ease of essentially a better language to develop your query, but you lose some efficiency compared to Dryad, where we have here the result for a Dryad implementation, which has really been hand-tuned. So that's really a trade-off. If you're really into performance, then you should put the time and the effort to write a Dryad implementation. But with Dryad LINQ, you can get the similar result, actually, by writing a tenth of the code. And this is actually the core of the query. It fits on one page. At the University of Washington, we have had some early adopters too, which I've looked at using Dryad LINQ to do large-scale spatial clustering. So they have simulation of the universe as it expands, and using computers, they generate snapshots over time. And those snapshots are huge. They have, in this case, 900 million particles, which are 3D points. And they want to be able to cluster them. So they had a previous implementation, and they looked at re-implementing it in Dryad LINQ, and they found that the development time was actually quite reduced, and the scalability of the system was good. They compared it to an OpenMP implementation, which by all accounts has not been finely optimized, and they found that the speed up of the Dryad LINQ implementation was actually quite a little bit better, and the scale-ups were very similar. No, not everything is perfect. Some of the things they wish for is a better way to partition the data. Dryad LINQ has some schemes to sample the data automatically and partition it, but for certain type of data, it will not be the most optimal, so they had to fine-tune that. They also wished for a better debugging environment, because to some extent you can do debugging on your local workstation, but sometimes things still fail on the cluster, and debugging there is still a difficult problem. Another example in a different field, this time in bioinformatics, which was done by folks at the University of Indiana, and I think they'll have actually a paper tomorrow, is an example of a problem that's what we would call pleasingly parallel. So you basically have a lot of data, and for each data set, data file, you want to process it using the same files, and the only issue you have is really parallelizing that as quickly as possible. And what's nice with the Dryad LINQ infrastructure is that you can really write a program which is essentially 2 lines of Dryad LINQ code and get that parallelization. And this is a comparison of several runtimes. So we have the Hadoop runtime, Dryad LINQ, and CGL, which is essentially a custom map-reduced implementation that the folks at Indiana have implemented. And you can see that all the runtimes are in the same ballpark. One of the findings there for the Dryad LINQ implementation was that in order to take advantage of the many cores using P-Link, Dryad LINQ, the version that we ship, that we give out for free download, using a community preview of P-Link, which is from June 2008. And that version doesn't work as well as the newer version of P-Link, which we have access internally, but you do not have access to them yet. So they had to be very careful with the data partitioning in order to get the P-Link framework to help them correctly. But we know that that's been fixed, and so it's a matter of time before this gets brought outside of Microsoft. Sorry?
How many nodes was that you said?
I believe this result is with 32 nodes. This is another example of a typical map-reduce problems in high-energy physics. Again, you have a lot of data files which comes from experimental data, and you want to write an analysis very quickly and test out your IDs. And so you have to do a first map, which is process the data, create an histogram in this case, and then aggregate the histograms to get the final views that you're looking for. And in this case, what we found is that Hadoop did not perform as well as Dryad LINQ. And the reason for that is that in Hadoop, there's a distributed file system. And in order to get that implementation to work, the analysis is done using not C#, not a managed language, but a special scripting framework called Root. And the problem with Root is that there's no implementation to access data which is stored in the Hadoop file system. Therefore, when you use Hadoop, you have to go from the file system to the file so that Root can access the data. And so that's really the cause of the inefficiency here, we believe.
Yeah, but Root could be modified to map directly.
It could be, yeah.
Who has done that? Is the people at the University of Washington?
No, this is the people at the University of Indiana again.
Oh, Indiana.
Mm-hmm. And this is another result, again, by a group at the University of Indiana, where this is interesting because it compares an MPI implementation and Dryad LINQ implementation. And you can see that for that problem, they're getting very similar result. But in order to get there, because you're using a completely different framework as opposed to MPI, you sort of have to rethink the algorithm that you're writing. So the problem is that we have a very large matrix of information about gene, and we want to compute pairwise distances. So in MPI, there's an implementation that is done, and if you try to do that using Dryad LINQ, it would not work because you don't have the very low latency that you can have in MPI. So what they did is they rethought the algorithm, and instead of looking at the matrix as one, they chucked it into blocks and then processed each block by on a vertex. And so by reworking the algorithm, you get very similar results, performance results. Of course, it's not a very fair comparison because we have different algorithms. So it would be interesting to take that algorithm that we have in Dryad LINQ and port it back to MPI and see what type of results we are. And so that would close my presentation. I wanted to acknowledge a few groups. Of course, there's the Microsoft Research Silicon Valley team, Dryad and Dryad LINQ team, and quite a few people have been involved in the project over the year. The Microsoft product groups, HPC group, and the parallel computing platform have been very helpful to our team, the Microsoft Research External team, which has worked with the two groups to put out that release that you can now download and try out for yourself. And last but not least, our academic collaborators from the University of Indiana, the University of Washington, and the University of Chicago. And those slides will be posted on the web at a later point, so there is a list of Dryad LINQ papers that you may find interested, and some other references about LINQ, P-LINQ, and the task parallel library. So in conclusion, I hope you're going to leave today with an understanding of what Dryad LINQ is. We believe it's a powerful and elegant programming environment that has a lot of potential for certain classes of science application. Of course, it's still an area of active research, so things are evolving, but we would welcome your involvement. I hope maybe some of you will want to try it, and if you have feedback, we would be delighted to hear it. So thank you very much. And I think we're planning for a short break.
You know what? Let's do it. I really believe in no death by PowerPoint, and we're going to do questions at the end too. But we have a little exercise after I want to do a couple more slides. And while we do this exercise, I think it's going to give an opportunity to everybody to kind of get up and stretch, and we'll do all that. So just give me maybe about 5 more minutes, and then we'll get into making it so you don't have to stay rooted to your chair. That's okay? Is there anybody that has any questions particularly on Dryad that they really want to ask right now while they've got it in their mind? Yeah.
You showed how arbitrary MapReduce program could be loaded in 3 lines of Dryad, which is nice. On these applications that you're testing, could you sort of compare that directly against KView, where you just literally take the function that they write, maybe translate that to C#? You can compare Dryad MapReduce to actual MapReduce, or was it always sort of a rewritten Dryad application? Is that clear? Maybe that's the question.
I'm not sure it's completely clear. No.
So you can implement all of MapReduce arbitrarily
right.
with 3 lines of Dryad code. Okay. So now you can given if I have these 3 functions or these 2 functions, I have now 2 choices. I can hand them off to Dryad and get them implemented directly in your 3-line program that implements MapReduce,
right.
or I can put them in the KView. Has that been compared on some of these applications directly, or instead was it always kind of a rewritten from scratch Dryad application using?
It was, I think rewritten is the answer. I can give you two examples of why you would not want to just take a MapReduce implementation and go to Dryad.
No, I'm sure you wouldn't. I'm sure it would be better. I'm just curious about the performance.
Right. There's an application called Cloudburst, which is again in the bioinformatics domain, which was implemented on Hadoop. And one of the people from the University of Chicago basically re-implemented that in Dryad LINQ. And so he started with what seemed like a 1-to-1 port, but then when you look at the details, then you realize that you're better off doing it differently in Dryad LINQ, because in Hadoop, because everything is MapReduce, in Cloudburst, for example, you did a MapReduce, but then you need to do another reduce. So what you end up doing is another map, which is an identity map, and then a reduce.
I'm just curious about Hadoop performance versus Dryad MapReduce performance directly.
Oh.
Yes, you have more opportunity to optimize things in Dryad, but without that variable, you'd be interested in just curious.
No. Well, the best we've done is rewritten the application, simplify it to fit the Dryad LINQ framework, and then compare the performances.
I have one other tiny question, I guess. You mentioned an internal language scope that was more SQL-like. What was the motive? Were there people that were asking for a more SQL-like language? Because it occurs to me that Dryad LINQ is already quite SQL-like.
Well, I think the scope came before Dryad LINQ.
I see.
Right. So. Yes?
In your algebra package that use Dryad, do you have a name for that? I'm trying to find it.
No, I don't think we have a name for it. No.
Is it something they can download?
I don't believe it's available for download. If you're talking about the one that was referred to in that big list, right? Yeah, it's not available for download yet. We'd like to work and make more stuff available. Takes time.
All right. Go ahead. Yeah.
For presentation, you emphasize that drawing the skill for the pipeline computation, where the data distributed in different nodes, and then finally it could be reduced to a certain node. My question is about whether if the computation of the workflows are not pipeline type, and the lots of data, intermediate data will be distributed in different nodes, how to manage those intermediate data?
So I think if you still have a pipeline and you're generating intermediate data, I don't think it would be an issue. You can just generate the data and say that data stays there and we're done.
Okay, so the data will be stayed in the distributed
Right.
nodes. And what if one node fails? How can the users get those data?
Well, the idea is that if there's a failure somewhere, the Dryad engine would back out and try to re-execute. And hopefully the second execution would work. If it always fails because maybe there's a problem with the system that's very deep or there's a bug in your program, then obviously you will not get the results that you're aiming for.
So when there's a problem happen, the data will be routed to other nodes, and there's some way for the users to get direct access to the data that routed to other.
Right.
Okay.
Yeah. Last one.
How does it interoperate with other non-Microsoft technology? I mean, non-Microsoft databases or non-Microsoft operating systems. Is it possible?
Well, at this time, all the implementation of Dryad rely on clusters that use Windows servers. So I guess the short answer is it doesn't operate at that level.
We have done some applications, though, where we're using open source, like the biology ones and things like that. They're open source executables, which are then distributed across an HPC cluster in Windows. So you can use other software, but it does run on the Windows HPC.
I was thinking about if you have already an infrastructure that, let's say, is a Unix cluster with a MySQL database, something like that. Can you use it?
Right. Well, I think that would be a fairly straightforward extension. I mean, because internally, again, that's not part of the public release. When I talked about having the ability to access data in SQL Server, of course, we're using Microsoft SQL Server in-house, but I don't think there's nothing in the implementation that's really tied to the server. So any SQL database would do.
Yeah, but I think, Christoph, probably the point is more if you can run on multiple platforms. So you can have, let's say, a Azure platform, cluster platform running Microsoft Windows, and a Linux cluster. So that I think is probably the most common environment that scientists are going to be set to find, because most of them run Linux cluster. Some of them have also a little bit of HPC Windows cluster.
Mm-hmm.
But definitely this mixed platform is probably there.
Mm-hmm. I mean, the best you could do if you had a Linux cluster, one thing that would be actually interesting in trying would be to instantiate Windows virtual machine on every node and then create a virtual HPC cluster. Then it would work. You may get into some performance issues, especially as you go through the massive data transfer that happen. But if you have an interest in doing that, I'd be interesting to even help you maybe.
All right. Well, I've actually kind of rethought my thinking here, and I think we have put you through quite a bit. So why don't we take a 10-minute break or so? Don't go by this clock. If you look at this clock, the second hand is moving about every 4 seconds. So you would have a 40-minute break instead of a 10-minute break. But please do go grab something to drink or use the restroom or whatever, and we'll be back by 11 and get started again. All right. Thanks for coming back, everybody. We're going to switch gears a little bit. We were just talking about, first we started with the infrastructure, what a data center really is, and then we talked a little bit about Dryad. Dryad is more of a platform. Remember that slide I said where there's this infrastructure as a service, platform as a service, software as a service. That first part was really about the infrastructure, the data centers, the amount of work that's involved in that, and abstracting that away from you, from your lab, or from whatever computation you're doing, and making that a service. Dryad is not really a platform as a service. You actually kind of download it as a platform, which you then use on the cluster that you happen to have. So we're going to talk a little bit now about what the cloud really is it's taking things like Dryad. All right, sorry about that. So we're going to take things that are like Dryad, a platform for doing your software, the software itself, and how all that distributes out. And that really is what cloud computing is. You can see that it's getting quite a bit of remarks out there in the press. Microsoft considers it, this is Bill Gates' language, but he calls it one of these big bets for the company, right? He always talks about, he's not with the company really so much anymore, but that framework is still out there for taking a really big bet, putting a large investment into a particular area. And obviously that's not for the sciences. There's a play in business here. The businesses will be wanting to use this, but we think that the sciences can also, obviously we think they can benefit from it because that's what our groups are working on. So this is an interesting graphic which I found out there. This is what's called the hype curve. Gartner Group puts together one of these every year. It actually puts together several of them in different areas. I don't know if you can read it very well. It's very small text, but you see right there at the very top of this big hype curve is cloud computing, right? What does that mean? That means that right now cloud computing is kind of getting a lot of talk, right? It's getting noticed in the press. All the CEOs of big companies are talking about cloud computing. But it's not necessarily, it hasn't quite gotten to what they call the plateau of productivity. We're going through its enlightenment right now. It's in the peak of inflated expectations. And I think that's actually fair. It's something which, Microsoft has to be looking out, and Amazon and Google, all these companies, they have to be looking at where's the technology going to be and what they classify cloud computing as this blue dot in 2 to 5 years. There are applications, scientific researchers need to be thinking out that far at least as well. So there are applications we can make use of it. But you do have to understand as we're going through this presentation that it hasn't settled yet. We don't know what the best patterns are. We're starting to get some idea of what those are. But we're just talking about kind of a preliminary view. We're getting the technology into place now where we can go through from hype to something that actually really is productive for actual day-to-day work. So just remember that as we go through this, that things are going to change a little bit. But there is some productivity to get out of it. You do see some of these other ones that I've been interested in, augmented reality, mobile robot, surface computers. They're not even quite up there yet. But they're all very interesting areas for us to be in. All right, so there's a lot of different ways to do a cloud platform. And different companies have taken different approaches. You can see that there's kind of a range here in terms of how much automation you happen to have and how much constraint you might happen to have inside of your application model. If you look at a service like Amazon's automated web services, it's much more of on this far end here with less automation, less constraint. Basically, what they're providing you with there, in case is it off again?
I'm going to switch those mics. It's
Okay. That's right here.
Sorry.
Basically, you host your own virtual machines. You put the code in there, you put whatever application. It can be a Linux-based thing, it can be a Windows-based thing. Basically, they're just saying you have this set of hardware in a virtual sense, and anything you program against that particular hardware we let you do, and we'll just charge you for how much you use it. Windows Azure, which we say Microsoft Azure here, is a little bit more limited in that it constrains you to a particular platform. It does the same thing Amazon does. It does actually instantiate the virtual machines that you're running on, but it also says here's some of the infrastructure work done for you. This is what we mean by platform as a service. Something like Dryad provided you, only more in a .NET application model, saying you can write programs against this. You have to conform to a couple of these interfaces. If you do that, you get the benefits of having triple replication of your data, failover services, things like that. And it's still, at least it's open enough that it says, basically, if you can write a .NET program against it or even an unmanaged program against it, you can still do that. But there's a little bit more management for you. Then there's even on the further end, there's more targeted things like the Google App Engine, and there's some that are actually, certain companies are actually written exactly for, say, a website that does sales of actual physical products, things like that. And what you're seeing now is that this is where we are currently, but the more I see where we're going as a company, I see this kind of stretching out this way, that there's more and more of a play towards having less infrastructure if that's what you want in terms of a platform infrastructure. And even Amazon is actually starting to add on to their particular programming model so that they're coming kind of into the space which we're taking on. It becomes more of a question of what your needs are on that particular infrastructure. And sometimes this is actually the best thing for you, sometimes that is, and I think everybody who's in this space is starting to recognize that and is trying to make sure that they cover the whole spectrum. But in general, the state of the art right now is that Amazon is on their AWS and their EC2 is kind of more on this side. We're kind of in the middle, and those things are fuzzy boundaries. Okay, so what we're going to do, I told you Microsoft Azure Windows Azure is a big bet. It's kind of like the future operating system in a data center for us, and we're treating it that way. We're giving it the Windows brand, which is kind of inside Microsoft. That's kind of a big deal. So I want to kind of walk through what it is to be Azure, how to use it, what's the basic programming that you might happen to do, what are the data patterns you use. Then we'll walk through a little more completely what the compute fabric is. The compute fabric is that platform that's doing the data management behind the scenes for you. And then we'll also talk about the data side of that. And there's three ways of storing things inside of Azure's basic data structures. And then last we'll get actually to what is kind of a more recent thing and just a recent offering, and that's SQL Azure, which is a fully implemented SQL database that's available through cloud means. Now, here's my caveat slide here too. We did announce Azure last year at PDC 2002, and what I'm trying to say here basically is that there are certain things which have been announced, and we've been working on other things, and there's a very good chance that very soon we'll be announcing more of those things, but I have to kind of limit what I can say here because that's what happens when you work for a big company. Yeah. So if you end up asking me a specific question about can it do this or that, and I start kind of humming and hawing, and I maybe point to this slide, well, just hold out. Pretty soon we'll know about all the full capabilities of the V1 release. So, but today I have to limit our discussion to what is available as of July 2009, actually, not 2008. Yeah. All right. So, traditional application programming. You go in and you write software against .NET or Java or whatever you happen to be doing. And when you write those programs, you actually have to tailor them to the capabilities of a particular system. If you're working on a phone, you might be using the same language, but if you're working on a phone, you don't have the same processing power you might have on your desktop or on a server. You might have more power for I/O or things like that. The idea with Windows Azure is to bring that up into this cloud metaphor. So what you want to do is still be able to write your .NET services as an application, but no longer, even though you want to maybe deploy these to these various form factors of computation, you still want to be able to write the same processing application. You want to be able to use the same data structure. You want to use the capabilities of a large storage system, even though you might want to display it on a phone. Things like that. That is the idea behind cloud computing in general. And what you want to do is make use of any services which are out there available already so that you don't have to reinvent the wheel. So the goal of Azure, obviously, is that it's a scalable and available environment. As Christoph was talking about with Dryad, one of the things you definitely have to manage when you get into computation, whether you're working with thousands of computers and thousands of data storage devices, is that something's going to go wrong. Things go wrong with our computers. It's pretty rare, but when you multiply it by 1,000, it's a constant thing that you have to deal with. And so what you want to be able to do is still be able to write your programs and not have to worry about that failure rate that's happening. Have the platform take care of that for you. And so it's always available, and in fact it's dynamically available, so that when you're out there in the field and you're starting to really roll out your tests and you need more compute power now, you don't have to go in there and rejigger everything. Now the interesting thing about Windows Azure is that it's not actually limited to C#. Most of the applications you'll see here, the examples you'll see here, things that we've written in the past are in C#. But Windows Azure does actually allow you to use pinvoke, which means if you're writing .NET code, you'd have to, in a managed environment, you'd have to block it out in an unsafe block, basically. But it allows you to invoke anything that you might happen to have. You can actually set up your computer in any way you want to once you've deployed that particular node. You can bring in a database that isn't SQL Server. We have an example of this, in fact, where we've used, if you're familiar in the BIOS space, there's a BLAST service, where you go out and you call BLAST service on a sequence, a DNA sequence of sorts, and then it goes and looks across a database to tell you what's similar. Well, we made an application that brought in a database, which is a custom database to BLAST. It has your own input data on there. You bring in the BLAST executable that was written in open source, but conforming to Windows, because this is running on Windows platforms. And basically, all you basically do is write a little .NET application that says on start. It goes in and calls in this BLAST interface on a certain subset of your data in the database. So the only limitation you happen to have here is that you don't have admin rights when you go and call your pinvoke, so that you can't get in there and mess up other people's virtual machines which are on the same particular node that you're running on. However, so you do have .NET, you can run PHP. We have examples of that. The team is actually supporting that. They, not just the research team, but the product team for Windows Azure thinks PHP, Perl, other languages, things that you wouldn't necessarily normally associate with Microsoft are going to be important for people who are going to be using this. And since it's important for web developers and for all the applications that's been written in the open source scientific community as well, we think that the fact that they're supporting these things will be helpful to this community. All right, so taking that illustration we had earlier and kind of blowing it out, basically what you have when you have Windows Azure is you have your applications which you've written, and they're no longer on one machine. They're now distributed across several machines. Running at the low level is what we call the compute fabric, and there's actually a storage fabric as well. And then all the compute side are actually, believe it or not, the compute stuff is running on separate clusters than the storage stuff is running in, but they all talk to each other really well, and there's separate fabrics for dealing with both of those and a common fabric for doing the communication between the two. So basically what you have to write is this orange stuff is an application which either talks to the compute fabric mostly or goes and accesses information from the storage site, and there's a configuration file which defines the various roles that your applications are going to run in. All right. So the fabric itself, when you're looking at the compute side of things, there are two kinds of roles which are common. One is called the web role, and one is called a worker role. The job of the web role is to face face the public, I guess, is what you say. You can write an ASP to page or PHP or CGI, whatever you happen to like to do. It provides, it's a service running in the background so that people can do HTTP requests to it. It'll provide a web page that will say, here's a job that you need to do. What inputs do you need to run that particular job? The user can come to that, enter in their information for their job. And what happens then is once they say submit that particular job, the web role is done. It then tells the worker roles that are out there that they need to pick up the information which was produced by the web role and get rolling with it. The interesting thing about the Fabric is that both things are scalable. So if you have a service in which hundreds of thousands or millions of people are hitting it all the time, it will spin up web roles as necessary in order to handle that particular load. If you have something where the web role is only to a small amount of users, but the work that needs to be done requires a lot of different nodes, the worker roles will spin up as necessary to handle those jobs. So that's the job of the load balancer that comes in through the HTTP requests, goes into what IIS is our internal, kind of like Apache. It's our web server technology. It takes those requests, turns them into ASP.NET or WCF or PHP on the web side, and on the worker side, it goes and invokes your code. Okay, so what's the details of how it runs? The implementation for Windows Azure is actually done in managed code. It's written using .NET 3.5, the first service pack, and all the libraries are available to you that you want to run your own code on from that. They are running in Windows Server 2008, the instances. There will be virtual machines on top of that, but those will also be instances of Windows Server 2008. It's a full trust user mode. So if you're used to administering these computers, that's what you have. It's not admin mode, but it's full trust user mode. Like I said, these are the services available to you. I didn't mention WCF, but so you have SOAP-based, REST-based, HTTP, all those things available to you. The servers themselves are stateless. That's the whole idea, is that you can always spin one up and bring in the information which you need. And they support the basic HTTP and TCP protocol stacks. All right, so how does the web role actually talk to the worker roles, and how do worker roles talk to themselves? So you start with a web role and your worker role that are defined. Then you have something called a queue. And this is a first in, first out queue, and this is one of the first class data citizens of Windows Azure. And basically what happens is when a web request comes in from the user, it takes the request that was made by that user and turns it into a very small message. A queue message itself can be a maximum of 8 kilobytes. So it takes whatever came in from the user input, and it might have to store, if it's a large input, it might have to store that large input somewhere else, but it creates what is a message inside of a queue that all the worker roles that are sitting out there ready to run are continuously looking into to see if there's something for them to do. And as this queue gets bigger or larger, you might end up having the Fabric take care of the scaling of the number of worker roles for you. So basically it reads from, it's first in, first out. It gets a message that comes in. It takes that message out, says, oh, I need to do something. You know, it's got 8 kilobytes worth of things that it tells you it needs to do, and that might be lookups into the data or not. And the worker role itself actually then can have the ability to post to that queue if it wants to have other worker roles pick up more information. In general, the pattern then that ends up happening is illustrated here. What you saw in this previous slide was kind of like how one particular worker role might, if it does one particular job, more of like a map reduce where you get all the maps queued up again. Azure goes beyond that. You can have worker roles which do several different types of functions. The first message comes in from this front-end web role. It comes in, spools up some workers, but they say they want to do other things. So there's multiple queues maybe going on. And this is posting to the original queue to have that same job happen, or maybe it then needs to do a reduce step like in the map reduce model, and you have a reducer queue that's over somewhere else, and then another worker role will pick that up. So you can actually get quite complicated graphs of computation going on. And the queues themselves are like everything else in Azure. They're actually fault tolerant. A worker role may pick up a message from a queue. It actually has a heartbeat to say whether or not it's still working on that particular message in that queue. If the heartbeat ends up at some point failing and Azure says, oh, this this thing that picked up that particular message off of that queue never reported back to me again. It has actually kept a durable store of the messages inside of the queue, and will repost that queued up message back to the queue so that another role will take it over. And so the queues do work like the glue and the communication glue, and then are in the end the resource allocation mechanism for Windows Azure. Okay, so now that's kind of the abstract thing. To me, I don't understand as well just in sitting and looking at a PowerPoint thing. Sometimes I like to have a physical demonstration of how these things work. So I've come up with an exercise, and I've never done this before. This is a workshop setting. I thought this was a great place to do it. But I want to see if humans can replicate a queue-based distributed computation system. And so I need some volunteers to help me out to do this. And I need lots of them, because I need a lot of worker roles. Okay, now first off, I need 2 traditionalists. Somebody who's more of a single processor kind of person. Okay, I need 1 more of those. No? Christoph is my other traditionalist. Okay, the rest of you, not everybody, whoever wants to participate, you have to be able to do basic arithmetic and have a writing utensil of some sort. So what I have here, this is a queue. What I have here, each one of these cards actually has a few numbers on it. All I need you to do is add up the numbers that are on this particular card. That you'll actually take it, this won't be your card necessarily. Add those numbers up, write the result here. The result then needs to go to another card. Now, you'll notice at the top, here's a 1. I need the result to go to 2 for this particular card. So I'll have a card like this sitting up here as well, where we take the result, write whatever your result happens to be on the blank line, the next blank line. As soon as one of these cards is filled up, like it's got 5 slots on there, put it at the bottom of the queue. Because this is first in, first out, right? So we want that to be at the bottom and percolate its way back up again. Now when we're done, the one that's marked 4 should have our answer for us, which will be the summation of all the numbers across all of these particular cards. Now, to get our traditionalist a head start, this is her card.
I'm actually seeing double, so this is not.
Oh, yeah. Then there's going to be a lot of them numbers. All you have to do is add all those up. Yeah. Huh? Oh, for errors? Yeah, we're going to see how this goes. Yeah, I will. I'll let you start because you've got a lot of work to do. I'm going to put the queue right here. Anybody who wants to participate, take a card off the top of the queue, add it up, find the number that you're supposed to go to, write it on that particular card, and if that card fills up, put that in the bottom of the stack. Okay? Ready for a race? I'm very curious how this works out. So go ahead.
Okay, I'm worried now that there isn't really an Azure infrastructure anyway.
Yeah, this is what we actually do. We have workshops and yeah. What I'm really curious about is if we get the right answer or not. Yeah. I should time it.
I would offer to do it on this, but I think I'd be.
Yeah. Yeah, that's not fair. I told you the answer.
Oh, nice. Yeah.
All right. Am I allowed to do parallel structure? Wait, I'm adding all these?
So when you're done with it, you can just discard it. I don't. Yeah. Okay. So we've got
What do I do now?
Take your result. Go ahead and write it on that one. Okay. Now this is now in our queue. So anybody who wants to take that can take that one. Yeah.
We can put it back in the queue so somebody else check it out.
Oh, we don't want to do that. We'll discard the message. Yeah. This is more worker nodes than I thought I was going to get, actually.
You need to work on your bus architecture.
Yeah. So yours needs to go on on one of the twos.
Yeah, I'm lost. Where's the 2 file?
Here. Another two. Now we need to sum up the twos.
Right. So this now goes back onto the queue. So anybody can take that one. And we got our first 3 back already. Good. So yours goes on to a 2.
Or 2.
So you should,
Collapse queues?
yeah, let's collapse this. So scratch that one out. Somebody's going to have to, yeah, there we go.
And that's different?
That's 3. Okay, that goes on a 3.
There is no way that this result will be real.
Well, we'll see. I know what the answer is.
Problem is that most likely people make mistakes.
Yeah.
Well, you know, one of us intentionally introduced a mistake about the system.
Oh, somebody, you took that before it was full.
Oh, there's still more?
Well, there were supposed to be 5 numbers on there.
There you go.
That's the last one. Okay.
Although due to community, they should
Now see, now you got to add 316 to this.
Yeah.
So here, put 316 at the top here.
Okay.
Oh wait, yeah, okay. $5,100. Okay. Is that what you got? It's not right. But the problem is we're actually missing one whole set of 2s. So there's 5 people that did 1s and maybe didn't necessarily write them down on the.
One of the notes failed.
Yeah, I had. Well, there should have been 5 of these actually. Yeah, that's all right. I didn't think it would work. Because the idea is to communicate how the function works. How are we doing on our traditional processing node?
Finished 4 columns already.
Oh, that's pretty good actually. Oh, that's all right. We'll see. They got the answer wrong, so you might get it right. I'll have to do this a few times and see if we actually get it right sometime.
Has anyone ever gotten it right when you?
This is the first time I've ever done it. Yeah. But now you kind of see how Azure works, right? The idea is that a message comes in. It says, "I've got this work to do on this particular set of data. This is your range of data." Now, what would actually, we'll talk about blobs in a little bit, but your range of this data would probably be stored in a blob somewhere. And the communication on the queue would say, go to this particular blob, get all the numbers inside of there, do something with them, take the result, and plug that into the next particular message queue. Or build it up on a blob, actually, and then when that one's ready, make a message out of that particular one. Okay, so while she's still working on that one, I got a little story to tell you. This is something I learned in discrete mathematics a long time ago, back when I was in school. There's an old wives' tale about Euler. You know Euler, the mathematician. This is almost certainly not a true story. That's how my professor presented it to me as well, but it's a good story, right? So there's this story that says when Euler was in grade school, his teacher hadn't prepared the lesson plan for that particular day and needed to do something with the students so that they would be taking up some of their time, doing something productive while she prepared for her particular lesson plan. And she thought, what I'll get them to do is to add all the numbers from 1 to 100 at their desk. And that'll take some time, and I'll have a few minutes to get ready for the day. When I heard the story, it was Euler. And it was still probably false, whatever. Yeah. Oh, yeah. So right, the traditional process, the point is that this can be done by a traditional processor very quickly. But so as the story goes, the mathematician, whoever you happen to pick for this particular story, comes up to the teacher right after being given the problem and has the answer, and the teacher goes, well, how did you do that, right? And he said, well, what I noticed was in the numbers from 1 to 100, if you take the first number 1 and the last number 100, you add them together, it's 101. You take the second number 2 and 99, add those together, 101. 3 and 98 is 101. So the answer is actually n plus 1, if n is the number that you're summing up, 100, times n over 2, which is having half the numbers. So the answer is?
4067? No. What's the answer?
The answer is 5,500.
Oh my God.
Yeah, that's all right.
What did Azure get?
Azure got 5,100, so we were both wrong, but that's okay.
It's 5,050.
5,050, excuse me. 5,050, that's right. Yeah. Azure was closer. They overcounted by just a little bit, but fortunately, we don't actually use like hamsters in a cart or people that came from workshops to run Azure. These are Intel-based products, or maybe AMD. I don't know. I can't give away with that. Right. It would be a computation doing this sort of thing. It would do exactly what we did actually, is that it queues up those numbers, goes and grabs them, puts them in it, and there's a little less human introduction of error. The errors we have to deal with are hardware based, for the most part.
Oh, I had forgotten the column.
Oh, well, that would do it.
So I got 5,120, which is much closer.
That's much closer.
That's much closer.
And in fact, that's really close to what Azure got too. Yeah. Well, Azure got 5,100, you know, so it was off by 50, you were off by 70-ish. Yeah, that's not bad.
So next to the fellow right beside me, he showed me that I had forgotten the column. So
That-
maybe it was parallel processing.
Yeah. That's good, that's good. You had a backup roll, double checking. I think we were within, like, you know, a factor of 10. That's pretty good. All right. So getting back more into the fabric itself. The fabric actually, and how am I doing on time? The fabric does have a lot of roles to play. And I'm going to have to go through it fairly quickly on what the fabric does. But basically, the important thing in the end is that you don't need to worry about this stuff. I'm telling you what you don't need to worry about when you're programming against a cluster, a cloud-based server like this. There's load balancing going on. There's switching going on for the data. Fabric controller needs to do that. So in essence, Azure owns the hardware and how to use that hardware and how to deploy things across that hardware. It needs to keep track of the resources both in terms of computation and storage and managing not just your jobs but everybody else who uses that particular data center. And it also has to do that across all of the, you know, those trucks that were being backed in there? Maybe you need all of those in a particular, you know, trailer, all those nodes. If you have to spill beyond that into a second trailer or a third trailer, or you have to spill outside of one data center and actually use something in Chicago and something over in Quincy, Washington, the fabric controller needs to take care of all of that for you. Fortunately, it also does have a logging mechanism and a reporting mechanism so that you know when things like that are happening. And if you really want to jump into the service, you can get the messages from that and say, wait a minute, I don't want the latency that going across two data centers would provide. Go ahead and just stay there. So yes, it's basically maintaining the health of the hardware. Fault tolerance is part of the big thing. Especially in rack-based systems and cluster-based systems, you will find that some faults are limited to a particular node inside of that cluster-based, the cluster where all the nodes are sitting. But you'll also find that there are node controller nodes inside of the controller. And when those things go down, that you have even more potential for failure because that can bring the entire cluster down. And so the purpose of the compute fabric on the fault domains is actually to find out when those faults happen both at single processing points and as well as controller nodes. And to make sure that anytime any processing happens on a particular message, that it does all of the backup necessary in case that failure happens. And in fact, it's a triple failure system. So if the first backup also fails, there should be a third one that's ready to kick in. And we test all of that stuff. And if a third one comes in, then I don't know what's going to happen. So when a fault does happen, there are update domains within the cluster and across clusters. And the idea is that These are sitting idle and ready to go when a fault happens on a particular node, and it's ready to pick up whatever particular job is. So if you allocate a particular worker node to do something, there's a certain percentage of those worker nodes that are sitting in the background ready to go in case yours happens to fail. And that will introduce some delay in the processing when you happen to have it, but that delay should be actually considered. If you have a large job that's going over a large amount of time, that should be a somewhat constant thing based on the number of nodes that you happen to run. So you can provide through configuration how much of a backup you actually want to have on some of these things, how much update domains space you want to allocate and have ready and available to you. But this can be also taken care of for you with the default settings. Then in the end, after you've written your program, there's another part of the fabric, which is the deployment part of the fabric. You write a particular program, you just say, I want it to be ready to go. What you actually do right now is you go to a particular front-end web system. There's a page which is actually, believe it or not, a web role inside of Azure that says that your code is ready to go, and it's a push-button deployment. You click on that node and get it ready, and it will report to you when it's ready to be rolling as your particular processing power. So this is the steps that it goes through. It allocates the nodes which you'd like, fault domains and update domains, places the OS. You can't configure that currently, but it will go through and make Hyper-V instances of virtual machines to go into there. It will configure the settings on those and get the roles started up. Those roles might have a kind of initialization phase where they're bringing in data for that particular computer. You're allocated, I believe currently you have, I think, 250 gigabytes of storage space and up to 1.5 gigabytes of memory on each node. So if there's anything you need to do to fill up that particular space, like bring in a database or something like that, you can get that ready and then notify that you're ready to run. And then from that point out, it's all about balancing the load that comes across and running your worker roles. The compute fabric does keep your service running, monitors the health, detects if it dies. We've gone through all of that. And it also detects if on the web role, if that's going down, and tries to recover from any failed messages that were going across the stack as well. So in case your hardware wonks, this is what's going on behind the scenes. There's definitely a caching system going on with and a caching and routing system going on that makes use of the best hardware we can find available to do that. It's actually commodity hardware for the processing. We try and get just lots of commodity computers doing the processing for you, but the networking and the bandwidth and all that, we try and make have the best throughput as we can using the latest switches, routers, and like. Obviously, in the background, there's also capacity planning going on. As there's more and more customers that come into a data center, we have to decide whether we need to move compute out of that data center and into another one. That's not something you actually control for the most part. There's people in those labs trying to figure out where the updates need to happen as we update the code and deploying that for you. This is more of a graph-based system, graph-based view of what's going on. Hyper-V is Microsoft technology for running virtual machines. It's been finely tuned for Azure. There's a particular hardware configuration being used inside of each of the plants. We were already seeing Hyper-V was getting numbers like 97% of what the processing time was on without using the virtualized machines on Windows Server 2008. And they've actually tuned it even a little bit more for this particular hardware. Yeah.
How does the I/O performance scale?
Across the nodes?
Or compared to the raw hardware?
So the I/Os right now is probably my biggest complaint with Azure. But we're actually, behind the scenes, we're looking at what they're getting ready to deploy as their first version, and it is increasing. But right now you're seeing, transfer rates for like a gigabyte are taking several minutes. But that's on that's before some of the caching is going on. You have to understand that behind the scenes, what are they doing? They're triple replicating your data across several machines. And you basically, I can't answer with hard numbers on that, because what you're going to be seeing, I think, by the time it releases, and even probably a couple months out, is that they'll be doing constant updates. So this is a good question to revisit as it comes out. Yeah. But yeah, I mean, there's a couple interesting anecdotes. Google right now will allow you to ship them hard drives so that you can get across and there's actually, I saw a very interesting article from South America where a particular telecom was having trouble getting data to go back and forth, and so a business which had data center, it had operations in 2 different cities in the same country down in South America. They were finding the data rate was so slow that they actually would put their data on these little chips like you'd have in your camera, and they'd attach it to a carrier pigeon and send it off from one center to the other, and they found that that was faster. Hopefully we can do better than that. I thought that would be an Onion article or something, but that was actually how they were operating. Okay, so some takeaways for it is that the VMs are just done for you. It's been an optimized hypervisor implementation for the hardware that's there. It's almost as good as running on a processor that has the configuration that an Azure machine gives you. 64-bit programming. There's logging built in for you. Desktop replication is in there, and that's all done through something they call the development fabric, which is really just what we were talking about earlier. It's the APIs provided. Storage is a big deal, and that's okay. So I got to go through this pretty quick. Storage. There's actually 3 types of storage. We talked about queues. There's also something that, if you're familiar with Google, you've seen something called Bigtable. We have a very similar concept, and it's not a full SQL table, but it's a key value pair relationship table where you can store a very long set of data. It's not like a relational database. There's no relational query language across it, but it's more like you would see in like a triple store. Blobs are where you would put the larger chunk of your data. Something if you were like trying to transfer from a file system, a large data file to get in there, you'd store them in a blob, and you can get stream writers and stream readers to go and read from those. Those are then very much easily to distribute across the computation, because each one of the compute nodes can go and access that particular blob data.
Sorry, blobs are key value? How do I retrieve a blob?
So a blob, you can actually, each one of these has HTTP REST-based access to them. You have a GUID that's associated with it. You put in your thing. That's the key that goes into it, and you can get that back down as a stream. But there's also inside of the .NET APIs ways of getting at your particular blobs.
I guess I'm just not clear what the difference between a blob and a table is. They're both sort of store arbitrary data with a key and get it back later.
Well, the table stuff is actually typed. It's things like you'd insert a string or an integer or things like that. It will go into that.
With a table, I cannot access it by any other attribute besides the key.
Right. It's the key for that particular table plus another key for the entry on that particular row, and then you get the value back. Yeah. And the blob is a stream. It's whatever. It's ones and zeros you can get. REST-based access through those things, like I mentioned. The access can be done through the API, or it can be done through HTTP on all 3 of those particular types of data storage. Tables are associated with a particular account. They can go across accounts, actually, if you set that up. They break down, this is what I was saying, that there's a key into the particular table, then basically into the entity, and then which is the row in that particular table, and then there's various properties inside of that row.
Excuse me.
Yeah.
So I can, from what I understood, queues are for processes and tables and blocks for data, or it's all mixed up?
Well, they're all data. In the end, there's limitations to a queue. A queue is meant to go away as a worker role picks it up, and it's limited to 8 kilobytes, right? A table doesn't have any relational store, and it does have a size limitation on each row. I can't remember what that particular limitation is. So really, they're used differently, but they have the same qualities in that they're all backed up. There's triple replication on all of them. And they're available across every worker node you might happen to have. The idea is to be scalable, and with the right, each one has its own particular application, which kind of gets to this question you're asking. Depends on what application you need for which one you're going to want to take and make use of. The Azure Developer SDK is available online. You can download it now. There's a July 2009 CTP available. It's actually a very small API, but for the most part you just redefine roles. They're objects called roles, and you have to implement an onStart method. And basically your code works inside of that onStart method and does whatever it wants to do, and there's a configuration file to say how many of those nodes you want at startup and how to scale it. You can also, inside of that SDK, you can run kind of virtual Azure on your local machine for doing debugging. And it will just basically run single processes inside of your machine and give you a way of monitoring through Visual Studio or for something else and taking the logs and seeing. So that you don't have to pay for the time to do your debugging, basically. This is what you would actually see. This is a configuration file, which what you're seeing right here is it's talking about the web role and one web role and one worker role. It's telling what the settings are for which ports need to be open. You can open many ports inside of there, but you have to tell it ahead of time which ports you want opened. You have to obviously put in your account name because there is a charge for using the service. Not right now, but when it deploys, there will be a pricing model. Right now, it's free. You'll actually see if you work with Visual Studio that when you install it, that it will set up these projects for you. It'll create a default configuration file, create projects for the web role, for the worker role. And what you're seeing here is actually one particular distributed sort solution for me. Here's a storage client project, a worker role, and a web role. There is one latest, kind of the latest thing that's out there. There's one more storage mechanism, and that is a fully relational SQL instance. This is more of a premier service, I think. It will cost more than the average input-output costs that Azure provides. But there is a full SQL Server implementation that's available through Azure, and it's being called SQL Azure. You can get a 1 gigabyte account, which costs you $10 a month. You can get a 10 gigabyte account, which will cost you $100 a month. But the service that you get on top of it is you can use all of what you would get in a SQL Server, well, not all of, but most of what you would get in a normal SQL Server instance, fully relational query mapping, all of that. So if your science or application needs to use that is available to you. 10 gigabytes is kind of small, but again, it's trying to run across commodity hardware, lots of instances, scale them up as you need to. If you need more than that, you can do transactions across multiple accounts. So there will be future implementations of other databases. You can actually write your own. We've done some, like I said, in that BLAST implementation. Bring your own MySQL over or whatever. It's as long as it runs inside of a role, you can use that. The advantage is, of course, is that it makes it for people who are familiar with SQL development already. There's something out there in the cloud for them to use, and it does have accessibility through the regular .NET and as well as other programming languages. So I'm sorry that I'm having to go through these pretty quickly, but we want to show one demonstration as well. This actually shows. This actually shows kind of the value of using the different kinds of SQL implementations, right? How much control do you want over? Do you want to be controlling your own, SQL instances partitioned across 100 different nodes? If you do, an on-premise, SQL instance it's perfect for you. If you don't want to have that overhead, if you don't want to have to be doing the updates, you don't want to pay for the database maintainers, then actually SQL Azure can provide a lot of value for you. So,
how do you scale? I guess where should they scale with the 10? Is that like once the 10 gigabyte limit is lifted or something?
Well, I mean, it depends on your application, right? Yes, for the first version, with the 10 gigabyte limit, you're going to have to do extra work if you have something over that 10 gigabyte to associate the data back and forth, the kind of partitioning work. But the idea is the more that they can do to get that limit increased, the less work you're going to have to do. And anybody who's currently operating at a size under that is not going to have to worry about that management at all. In fact, the best pattern probably to use right now is to index your data which is stored in Azure blobs, right? So if for instance, you've like in an oceanographic scenario, you've got a bunch of netcdf files, and they describe a particular area in a particular time, you can get that indexed into a SQL Azure database, right? You can do interesting queries on where the data actually that you're most interested in is going to live. And then instead of having to scan through all of your blobs that's in there, you can actually go do that query over here, find out where the interesting data is, just get the relevant blobs and work with those. So big data can live in the blobs indexed over on the SQL Azure. This is what's in scope and not in scope for V1. That doesn't mean that they won't be getting the distributed transactions and CLR support, things like that. They will be getting to these. These are very important scenarios for them. But, there's, like everyone knows, when you write software, there's time constraints and resource constraints. But what you will have is triggers, table variables, built-in stored procedures will be available. Your own stored procedures won't be right now. That's what the CLR is getting to. Okay. The takeaways on Azure is that it's always on, it's distributed, it's large scale, your applications write it once and it deploys as needed. It manages both your services and servers. It's the infrastructure as a service, platform as a service, software as a service. We do have a demonstration. I'm going to skip the phylogeny. That's something we wrote. I would rather show in the time we have left something that's been written outside of Microsoft to show you that research can make use of this. So we're going to bring up the Newcastle guys, Paul Watson and the rest of the team, and they can show you exactly what they've been working on using Azure. And I think here, you guys might want to use this, because they're... You can just even pass this around and use it like a mic.
Hopefully the magic wire works. I'll grab it when you finish speaking. Sure. Brilliant. Okay, what I'm going to show you is some early results from a project that's actually been funded by Microsoft Research. And that's to try and use Windows Azure to support some drug discovery work that's going on in Newcastle. And the main focus has really been to support the science of people in Newcastle. So what we have is a platform that's partly on Azure, part of it runs on Amazon virtual machines, and part of it runs on our own servers. So what we've used is Azure to support some existing infrastructure. And what we have in Newcastle is a group of people that do something called Q-cell modeling. And the idea is that you can relate structure of molecules to how they actually perform against virtual diseases. The idea being that it's very hard and expensive to measure the activity of something, but it's relatively easy to do something related to the structure. So the idea is you build a model relating the structure of a molecule to how well it treats a certain disease. And a simple example of that, I mean, you can't actually do this, but you could try and relate the shape of a molecule to how well it'll attack cancer. So you could say the effectiveness is approximated by the length and width of this molecule. Now there's hundreds and hundreds of descriptors you can calculate, from sort of different types of bonds to how the electrons move around molecules. And you can use these to build up like fingerprints of molecules, and then take those against existing databases of compounds that you know how well they perform, and sort of build up an estimation, say, given a molecule with these characteristics, it's likely to have this kind of activity. And the reason we do this is to reduce the search space. So if you have sort of 10,000 new compounds, you can't screen them all. So the idea is that you'll take these models and say, of these 10,000, these 10 are the most likely to work well in my sort of situation. I say there's loads of descriptor calculators, and there's many databases. People have private databases. There's things like PubChem. Wombat's a database that has lots of cancer research data in it. And a group in Newcastle use their own bit of software called Discovery Bus to manage all of this. And what it does, effectively does an exhaustive search. So it has a list of all the descriptor calculators you know, all the molecules you have, links to all the databases, and it just churns away constantly building models. It's an agent-based system, so we have one manager node with I think it's an Oracle database on it, and a number of worker nodes that know how to calculate descriptors. So as soon as you add a new descriptor, all this stuff gets kicked off and some models get built. Now we've just got a new installation of it. A few weeks ago we put 100 data sets on, and the last few weeks or so we've got about 15,000 models built. So it runs all the time and it does a lot of work. One of the nice things about it is it's, like I say, it's continuously running. So as soon as someone comes up with a new descriptor, it gets put into Discovery Bus and all the existing models get rebuilt. So you always have kind of an up-to-date set of models relating your compounds to activities. The drawback of that is it's really hard to add models to it. Until recently, it was run by one guy in Serbia. And to get a new model, you have to email him and get his blessing to install it. And it used to take weeks to get new things added. So we've basically got two aims, really. One is to make use of cloud infrastructure to actually be able to make more models. And secondly, to actually make it easier to add agents. So the way we want to do it is we've got this application called eScience Central. And what this is a kind of collection of all the services we've been building in Newcastle over the years to support eScience. So we've got basic things like security, workflow enactment. We've also put some social networking in there so people can share data and models. And we've built this on top of a cloud infrastructure. At the moment, it runs on Amazon nodes. We have some of our own machines as well. And this project helped us to bring in Azure to do some calculations as well. We have an API to it as well, which is REST-based, so we can plug in other applications. It's a bit like Facebook. So you can write an application and have it use eScience Central data. Our workflows can use code written in Java, R, which is an open source language for stats. It's got thousands and thousands of packages in it. Octave, which is a clone of MATLAB. .NET as well. Now we're using Azure. We can do some services in .NET. Our REST API, we've got some work that was done with Dryad actually recently to visualize some of our data on a Microsoft Surface. Silverlight, so we've got some monitoring applications which we'll show you in Silverlight. Some basic work sort of using phones to visualize data, and some very early sort of Office plugins for all of this. So what we're actually trying to do is to build a workflow. This is a very simple one there, and use that workflow as an agent for Discovery Bus. So instead of going off and doing all its work in Perl, it'll know to go to eScience Central and run this workflow to do some calculations. So by doing that, we sort of send requests for calculations into eScience Central, then we use eScience Central to scale that out over Azure. And what we've managed to do at the moment is not only .NET, but the code we're showing is using Azure to run Java. We've ported R to Azure, so we've got that running. I think we're doing some work with Python as well. Also, we've managed to dynamically deploy some code. So the first time you run a Java job, it'll install Java on the virtual machine in Azure. And we've got some work on role monitoring as well, which we'll show you.
Did you design your own workflow engine, or are you using some specific workflow engine?
We have one that we've had for a few years. I wrote about 4 or 5 years ago. At the moment, we want to use Taverna, another workflow engine. So the idea is we've got this platform that supports a load of different engines. So we want to be able to put anything into there. So this is the architecture. This is kind of a preemptive excuse for the demo, really. We're running on 3 different systems. It worked 5 minutes ago, but that's a long time in demos. So we've got this green stuff here is the Discovery Bus architecture. So we have our top node there that does all the management, agents here. And what we've done is we've built a little agent there that sends requests off to the orange part, which is eScience Central. And that in turn runs code on Azure. So that's what we're going to show you. And there's 4 basic things we're going to cover. Firstly, creating a workflow to act as an agent. Then we're actually going to tell the Discovery Bus that there's a new agent that it can use. And as soon as we register it, we'll see it actually start to use the agent and put work through it. And then show sort of scaling that over multiple nodes on Discovery Bus. So do you want to? Now Simon's going to click this because he's better at clicking than me. Do you want to? That wasn't going to work, was it? it doesn't need that, it's okay. Let's have a look at that. Oops. Just grab that a second. So, we'll use that a second before that comes up. That was just going to crash, wasn't it? That's okay. Yeah. There you go. Okay, do you want to log in? Should have. Okay. So first of all, log in as Simon. Okay. So this is eScience Central. So first of all, we're going to go to the application to start a monitor application. This shows all our nodes on the Zio and how they're actually operating. So we'll go to that. So this is a Silverlight application here, and what we're showing is our 10 worker nodes, I think. So there's memory usage there, there's CPU on the top left, and there's a history of both of those. So at the moment they're doing nothing. Yeah, sure. Okay, so these are the workflows that Simon has at the moment. So if we could add a new one, yeah. He's doing it, it's just taking a... The joys of wireless networks and demos, eh? I don't know, it seems like it's frozen there. Sorry about this.
The workflow editor is a Java app, but so I suspect there's some network problem trying to access that.
Probably should have written it in Silverlight. I was doing something. To try on yours. Try on Safari. That just died, doesn't it? Yeah. Yeah. Oops, I come out again. Okay. It's looking more promising. It's coming. This is just, yeah, like I say, carrying it from there to there, obviously made something happen. Yeah.
Well, you guys are going to be around.
There we go. Thank goodness for that. Right. So was that as well. Right. We do. It's adding them now. Okay, this is the basic workflow editor. So the services are down the left-hand side here. So we're going to give it a place to load data in. We're going to do an Azure calculation, and I'm going to export that in a form that Discovery Bus will recognize. And then I get some pictures of molecules as well. So we just join these services together in here. So this block here goes off to Azure to calculate some descriptors. This imports data that Discovery Bus has sent, and then exports it again. So, okay, so you need to set it so it recognizes that input. Sorry? External source needs to be set. Okay. Right, so that's created the workflow that Discovery Bus is going to use. So you can see the input there. So if you go to the runs, so each time it runs, you'll get a new run appear there, and there's nothing, so it's not been run before. So we go into our applications again. Yep. Like our resource mode. Oh. Firefox had that in, didn't it? There we go. It's basically killed it, hasn't it? Okay, anyway, so we're installing Discovery Bus, so that's the workflow we just created. And there's a list of things that it recognizes here. So these are all the calculations that it knows how to do. This workflow does calculate descriptors, so we'll tell it that. Tell it the input and output file names. Pick the workflow we want to run, so that's that one. Okay, so that's actually gone to install that in Discovery Bus. So when that's finished, it'll know that is a new agent. So if we go back into workflows, go into there. We should see that it's actually starting to kick off runs. So that one there was started by Discovery Bus, so it's called that. And that really has, yeah. Complete crash of Firefox, wasn't it? Do you want to force quit that and then? It just works on a Mac, which I've always found very good. It's very nice. This is.
Yeah, probably felt a kind of unfriendly environment.
It's just being too helpful to us, isn't it?
But I like the mess. That's what Simplus can say. Oh, that's a great thing. This is not cool, but you're going to this software. You put the screen. Green screen, definitely yellow smile.
Okay, we're back. So this is hopefully. Okay, so what's that showing? It's showing one worker node in Azure is being called because we set our workflow to use one node. And the other nodes of the 10 are doing nothing. So that's done 2 runs of that now. How many does it actually do?
Do 4.
4, okay. So if we set that to use a smaller chunk of data and run it on 5 workers instead. Didn't save. Yep. So I have to get through all 4 before it'll do the...
We'll do the next one.
Okay. So the next time that's called... not being called.
No. Trying to force something through.
Yeah. I'll force some data through this instead. Save. So if we run that with more data,
It's exactly the same data and exactly the same workflow, it's just we forced it to run rather than Discovery Bus kicking it off automatically.
is it though? It is running, isn't it? Yeah. There we go. Excellent. That's 5 machines running that one, yeah. Which, yeah, you can see the speed up there. There's obviously some overhead in passing messages around, but we could make it like that. Okay. I think that's, yeah, kind of demonstrate. Cheers.
There's a, I don't have a mic now, but. That's about it. I'm going to spare you the last slide. It's just a bunch of links. Please go do when you're done with this. If you're interested in Azure, go get this slide deck. There's a lot of resources that are available. I'll just mention right now you can go to microsoft.com/Azure and you can sign up for an account. You can use that until we actually have released a version 1. It's all free to use and experiment on right now. It's considered in consumer technical preview mode right now. CTP, that's what it'll show up as. And I highly encourage looking for what is called the training kit, the Azure training kit. Inside of that, there's probably 10 PowerPoint presentations, one on SQL Azure, one on blobs, one on the compute fabric. There's several videos showing how to interact and create your own project, things like that. So if you have further questions beyond what we've talked about here, that training kit will have quite a bit of the answers for you. All right. Are there any questions before we're all done? We're past our time. It's already 8:15. Yeah. But I'll answer any question, or you can come up and talk to us, and we'll do it individually.